And we are going to continue with the talk by Minal from Netflix, who's going to talk us about how they scale delivery of client applications at Netflix.
The relationship between the speed of an automobile and road safety is a heavily researched subject. Even without delving into the statistics, we are wired to attribute an increase in accident risk to speed. And we carry this perception with us in software development. We tend to correlate the risk of shipping poor quality application to the speed of development or frequency of its releases. This translates to more frequently that we release an application, the higher the probability of bugs in the software we ship. Good afternoon, everyone. My name is Minal Mishra, and I'm here to tell you about how we manage to counter this perception and scale the delivery of client applications at Netflix. I have been part of digital entertainment products for the past 15 years, some of which include games at Xbox, music with Zune, and videos at Netflix. And if you don't know what Zune is, then you clearly have not watched Guardians of the Galaxy Part 2. Netflix is available for streaming on thousands of types of devices that live across a wide spectrum of CPU RAM capabilities. If your toaster had a screen, I'm sure we would figure out a way for you to watch Netflix on it. This introduces a challenge on how to ensure Netflix users get the best application experience irrespective of the device that they're using. The same client application runs on a high-powered gaming console and a low-powered streaming stick. Our aspiration to release frequently makes it a challenging endeavor to test across all the hardware and firmware combinations. This makes it important for us to supplement the release decisions with signals received from the field during the delivery process. Okay, don't worry, the spinner is not in your VC application, but just used to illustrate and highlight the fact that if we don't enhance our delivery process, there is a likelihood that a client application on a certain device type can have higher load times unbeknown to us. Or worse, they could be experiencing poor video quality due to an application bug, once again without our knowledge. There are two types of client applications. First, one that we control, such as the web player JavaScript application illustrated here being downloaded from a CDN before playback starts. And a similar client application model is used for Netflix on TV devices. The second type of client application is one that's hosted behind an app store, for example, in mobile phones or even game consoles. I'm sure some of you are wondering, they have likely addressed the challenges with frequent application updates, so why not just adopt their model? App stores use a staged release model. Under this model, an app update is released to customers in stages instead of all at once. There are two main benefits to this approach. First, if something were to fail catastrophically, the release can be paused for triage, limiting the number of customers impacted. Second, backend services and infrastructures can be scaled intelligently as adoption ramps up. This is a graph of a counter metric which exhibits version adoption over the duration of a stage rollout. There is a gradual increase in percentage of users switching to N+1 version. I'm using playback start counts here. The fact that user can start playback suggests that their transition to the new version is successful, and there are no evident big red flags. However, if the user takes longer to start the playback or receives an error while trying to fetch additional streaming chunks, that is not reflected in this metric. So here is a normalized sensitive metric, like an error rate, during the same period for the two versions. What you notice is that the metric for n+1 version stabilizes as the rollout ramps up and reaches closer to 100%. It is then you can compare n+1 to the time-shifted metric of version n when it was at 100%, few hours or few days ago. If we try to compare the metrics between at any time between those two periods, we cannot confidently spot a regression. On this chart, we compare a median play delay metric for the two versions over the same period. This is reported for every playback initiated by any Netflix user. The pattern is similar to what is described in the previous slide, even for a typically robust percentile metric like median play delay. The alignment that we seek in the metrics between the versions is achieved only when n+1 version reaches most of our users. I'm going to risk dating myself and explore an analogous example of using dial-up internet to download an image from the 90s. The image would slowly reveal itself looking pixelated initially before finally downloading completely. Think of the metrics derived from the phased new version of the application as the number of pixels in an image. More pixels allow for a better identification of the features inside. So the current version available to a larger population has a better resolution than the new version that's rolled out to only 5% of the users. We can squint while staring at both the images and argue that they look similar. And a few days later, when you reverse the adoption percentage, the version n+1 is at 95% and version n is at 5%. Side-by-side comparison indicates that the images still look almost similar, but when we time shift and compare a metric at 100% for both the versions, we realize that something was missed, like the bird on the kid's backpack in the images. To summarize, staged rollouts have a lot of benefits, but there is a significant opportunity cost to waiting before the new version reaches a critical level of adoption. In order to derive the most out of staged rollouts without a lot of squinting and comparing metrics, there have to be significant investments in advanced analytics. So we brought science of control testing into this decision framework by using what has been utilized for feature evaluation at most tech companies. The main goal of A/B testing is to design a robust experiment that is going to yield repeatable results and enable you to make sound decisions about whether or not to launch a product feature. But that is not what we're trying to do over here. We are A/B testing the entire application. The new version may include a user-facing feature which is designed to be A/B tested and resides behind a feature flag. However, most times it is adding new obvious improvements, simple bug fixes, performance enhancements, productizing outcomes from previous A/B tests, logging stats, etc., that are being shipped in the application. If we apply the A/B test methodology, or client canaries as we call them, to differentiate from traditional feature-based A/B tests to the image metaphor, The resulting images at 5% allocation would look like this for both the versions at the same time t. It is easier to visually compare them and even apply statistical inference to shift the conversation from we think to we know. There are several differences between feature-related A/B tests and incremental product changes used for client canaries, but the main distinction is the shorter runtime and multiple executions of statistical analysis, sometimes concurrent with the allocation. The runtime is predetermined, which in a way is a stopping rule for client canaries. Unlike feature A/B tests, we don't have the luxury to collect evidence over several days. But it is important to run A/B tests over several days to remove any bias and encapsulate an entire business cycle so we can truly justify any lift from the new treatment. There are other notable differences as well, which I will share as we go through the different stages of an A/B test and how they map to client canaries. Over here, we illustrate the three key pillars of an A/B test for a client application. They are allocation, metrics, and analyze. We use orchestration to connect the client application to the three pillars. This reduces the cognitive load of frequently setting up and executing tests for client canaries for an application. Let's dive deeper into each one of these. Allocation is the first stage once your new application has been packaged and tested. As is of the essence here, we rely on dynamic allocation and allocate users who come to the service during the canary period based on a set of pre-configured rules. The A/B test unit to sample has typically been a user who is a Netflix member, but for client canaries, anonymous ID works better as that allows us to evaluate non-member experience too. The other possible units are network traffic, page views, playback sessions, but those are not an option for client canaries. Our allocation rate is very high since we want to reach our desired sample size sooner than later. Even though allocation is random, there is bias introduced due to the canary time constraint and high allocation rate. For example, if the canary is run in the morning, say Pacific time, most users sampled are from countries where it is Netflix prime time, ignoring users in other countries who might exercise a different code path. Even though this is a powerful methodology, it's important to be aware of its shortcoming for our use case. Next up are the metrics. We spent most of our team's time and effort in this space. The metrics to evaluate canaries are derived from client logs. These metrics are aggregated in real time from streaming events versus in traditional A/B tests where this is not really a requirement. Due to its large volume, the data aggregated is at 1 minute granularity. And some of the metrics are also available as summary of the user's session. This is different from the offline aggregation, which is used for A/B tests, where aggregation happens at the user grain to remove any, say, frequent streamer bias. Distribution and percentile metrics for streaming events are also approximations as opposed to offline aggregation. Another reason to not completely rely on this system for feature evaluation, even though there might be an inclination to do that. In, in order to increase adoption of the system that we have built over here, we needed to provide a simple path for client developers to contribute to real-time metrics as they are best familiar with what needs to be monitored. A/B test analysis is a very vast topic and can be an entire talk in and of itself. Over here, I'll just aim to highlight the differences between the analysis for client canaries and feature evaluation A/B tests. In A/B tests, we try to reject the null hypothesis. Whereas here, in a way, we want to accept the null. Since we do not expect the canaries to move any metrics, we try to check all possible application-related metrics. Whereas in A/B tests, we expect to move some evaluation metric such that we can confirm that the treatment is effective. There is, however, another flip side. A sufficient statistical power is imperative for achieving meaningful results. And sample size influences statistical power. But since we are bound by time, we can only realize a sample size feasible during the time period of the canary. This means our tests can be underpowered, or in other words, can only detect very large effects. And it's good to be aware of that. We use classical stats inference for our analysis, but are also beginning to explore sequential tests as it might be more amenable to our use case. A continuous delivery discussion would be incomplete without a pipeline visualization. This is the delivery pipeline of one of our client application. We have several custom stages to interact with our internal A/B infrastructure and application configuration to set up the A/B test. And the start canary A/B test stage starts the allocation, followed by 2 phases of real-time metric analysis. The first one contains key application metrics, and the second phase has additional metrics, which may be sensitive to initial noise, and hence it's done after the first phase. Since we have connected client canaries to our A/B test system, we can even analyze offline metrics, which can provide another perspective, including, like I mentioned before, remove the frequent streamer bias from the real-time data. This is followed by a regional rollout to protect us from service outages due to any potential increase in load by the new client version. We have been tracking the client canaries we do in production for the last couple of years. As per this chart, which shows cumulative counts of client canaries since 2018, there has been consistent growth in the number of client canaries that were initiated. This growth indicates over the years, client teams have become more confident in the system as they often canary test their applications. And the other important question is, how often do these canaries detect regressions, which makes the client teams roll back their application? This chart shows the year-over-year cumulative counts of rollbacks when a regression was detected. For 2020, we did 60% more canaries than the previous year. And we also added a lot more metrics that were monitored in those canaries. Additionally, we were doing more rollbacks than patch forward, significantly increasing the rollback cumulative counts. But the main thing that is broadly observed here is that between 5 to 10% of client canaries result in a rollback because we regressed a key metric. And so if we didn't have the current system in place, we could have potentially exposed our consumers to these regressions. This is just the beginning for continuous delivery of client applications at Netflix. It is a fast evolving area, and there are several interesting problems in this space still looking for solutions. Should your interests align with this, please do connect with us. And thank you all for listening.
Thank you so much, Minal, for the presentation. It's an interesting technique that you're using. I also was always fascinated about the simplicity of the statistical analysis that Netflix always tries to employ with such a high efficiency. So it's not so much about advanced techniques, but it's about what brings the most value. And so the question I have, it seems like what you have in terms of setup resembles quite a bit the progressive deployment technique, which is like the continuation of continuous delivery. I think it's one of the techniques that essentially allows us to safely test in production, because you can incrementally ramp up each feature you deploy to a point where until it's 100% deployed, or until you detect some sort of regression and you automatically roll it back. So I have, I guess, a few questions. First of all, do you just always use this approach? Like whenever you deploy a new feature, you always automatically just assume that it has to be gradually ramped up, or developers still have to request some sort of manual action?
First of all, thank you, Taras, for organizing this event. I think, considering the times, it's great to see such interesting topics over here. To answer your question, there is the delivery of the application versus delivery of the feature are kind of modeled behind an A/B test. So what effectively we try to do is when you do the rollout, whether you're doing of the application or whether you're trying to do for the A/B test, you want to make sure there is a sampling done for both control and treatment. And that helps you basically compare the health of the application or the health of the feature in the field based on the metrics that the client is sending to the service, right? And so since we've started, since we built this pipeline in place, most of the A/B tests for the client applications that we have, or even releases, is using this model. That way they get a signal from the field in terms of whether the features or the new code is performing well, or is there a regression in any of the metrics that they monitor.
I see. So is this only used in the context of A/B testing, or you also can just use it in the context where you, for example, as a developer, and whenever I ship a feature, I just defined an SLI for that feature. So let's say an error rate, or maybe some sort of invocation count, and then I also define an SLO to decide whether those SLIs are within the range of my expectations, and based on that, you either proceed with the rollout if all the SLIs and SLOs that I have defined are within the range, or you automatically just roll it back.
Yeah. So go ahead.
Yeah, no, I just want to say that basically, so is it only for a B context, or this is also the use case that you said?
Right. So the metric definitions are handled by the client developers. So they have the freedom to define the metrics. The metrics can be used in two ways. One is to monitor the release, and the other is just to monitor generally the application in the field, how the health is. And if there is any issue, say, the operating system under the app did an upgrade, and that might lead to poor performance of the application itself. So you need, these metrics will also help you catch that. And so you build alerts on top of that to be able to see that those problems. But when you're monitoring the release itself, you're just reusing the same metrics, except instead of having thresholds, you're comparing the metric of the new version with the same metric of the previous version at the same time instant. And that way, if your metric is shifting from the previous version, and if there is a diversion, then that's something which is unintentional. Then it is something for you to kind of investigate and identify whether it was related to your code change or whether it was something that you expected the metric to shift.
Awesome, thank you. I actually have a bunch of questions about like how do you define the SLIs and SLOs, like because you mentioned that developers are actually able to define the metrics they care about. But I hope that we are going to have a chance to talk about this during a panel discussion, because I think it's going to be like the standardization is pretty much going to be the theme of the panel, looks like so far.
Mm-hmm.
So yeah, so thank you so much, and I hope to see you in, I guess, 20 minutes.
Sounds good. Thank you.